I would love to take a moment to introduce you the project and myself. My name is Katya Loginova, and I'm a project coordinator of the WiNoDa project. So WiNoDa of English stands for Knowledge Lab for Natural Science Collection and Object-Related Data. I'm very happy to see so many people joining us, and while others are joining, can you please write a plus to the chat so we can understand how many of you were at the first webinar? Yeah, so we are now starting our 2 days, not 2 days, but two rounds session on machine learning. So today it would be a brief introduction to the topic. And the next time it would be hands-on session, but please pay attention that the next time will be not in 2, but in 3 weeks. So not on 29th of October, but on the 5th of November. Yeah, for the next webinar, as well as the whole round, I just remind you that you need to be registered. And in a moment, I will send you the links to the registration to the chat, so you can have this on your hands, as well as some important links, such as to our website, to our LinkedIn page, and so on. And one more important announcement is that we are going to have a workshop, Decoding Berlin, in November. So you are the first people who are going to be familiar with this information. Yeah, so if you are in Berlin or you are going to visit Berlin for this workshop specifically, you are very welcome. It would be a hands-on experience on working with data from museum collections, namely Museum für Naturkunde Berlin. And you get the access to the historical, museological, archaeological data that we have. And this will be a very fascinating event for us as well. So you are very welcome to join. And that being said, I would love you to be introduced with our lecturer today. It's Dr. Tim Conrad. So those of you who were at the first webinar have already met them, and he's the head of the with the Visual and Data-Centric Computing Department at the TUSE Institute Berlin, and also head of the Medical Bioinformatics Research Group at the Freie Universität. Okay, so that being said, I would love to give the floor to the team, please. Yes.
Hello. Well, not good morning anymore, but yeah, almost a good afternoon. Let me try to figure out how to start and share my presentation here. And I need to share this. So that should be visible now. Good. So welcome to the second session. If you didn't join us for the first session, don't worry about it. That was more like a general introduction to data science. There is not much, at least, that is specifically building on that. Today is more like a standalone thing. There will be 2 or 3 references to last week where I introduced some concepts, which I will not explain in too much detail today, but at the end of the day, everything should be understandable. I tend to go through my slides in the speed that I think is necessary. If it's too fast, please just interrupt me. If there are questions in between, please ask them directly. I will not monitor the chat because there's too many windows here. But please just unmute yourself and scream at me, and then I'll make a little break and try to answer your question if it's possible. Towards the end, we should have some minutes also to discuss or to ask questions or to answer questions in the best case scenario. But once again, please, if they're in between, just shout at me and we'll take care of that. Okay, good. As we just said, this is a serial of classes or of webinars. Last week was Introduction to Data Science. This week is this brief introduction to machine learning. And then next session, next week, will be the hands-on part of today. So we will actually try out some stuff that I introduced today. And since it's a hands-on project, you will actually have to do stuff yourself. To allow you to do that, you will need a Google account because we will use something called Google Colab. If you're familiar with that, good. If not, don't worry. Also, that will be introduced briefly next week. Oh, not next week, on the 5th of November. So yeah, there's no need to make yourself familiar with that. Just make sure that you have a Google account. If you don't have a Google account, also don't worry. You will just not to be able to do the exercise yourself. But I will also repeat them and show what was supposed to be the outcome of that. But it will just be a little bit boring because in these 10-15 minutes, people do something. You will just sit there and watch them. Yeah, anyhow, so please next time bring your Google account. Now, machine learning. There are, I would even say, hundreds of definitions, if not even more, that you'll find on the internet or Wikipedia or wherever else. I grabbed two now that I think are more or less summarizing most other ones. The first one is by NVIDIA. I actually didn't really find out the year they stated this. However, they say machine learning at its most basic is the practice of using algorithms to parse data. So look at data, basically learn from the data and then make a determination or prediction. And this is what we also discussed last week a little bit about something in the world. And by world, of course, now everything is meant from the world your data lives in to the actual real world the data comes from and you would like to do some prediction about. Last week, we were then also discussing something about being actionable, as in these predictions should be somehow connected to something that you can use it for, but at the end of the day, that doesn't really matter. Okay. When you then talk about learning, also another question could be, well, why do we need to actually learn something, or what is this learning really connected to? And then let me give you the simple idea or the basic idea again about that. And the specifics might differ, of course, but oftentimes learning is used when, and this is the first thing here, human expertise does not really exist about a particular problem. Think about navigating some robot on some faraway planet, or something that is also often happening when you sometimes talk to medical doctors and they come to some kind of medical diagnosis and you ask them, wow, how did you get that? That was not really obvious from anything, but hey, you're correct. Then oftentimes, well, it's not true, but sometimes medical doctors are not really able to explain their expertise. It's something they learned during the long studies and from the intuition and from working with patients, but it's hard to put into rules. It's not really, if temperature is above 38 degrees and this and this and this, then it's this disease. It's often a lot of things that come together, and medical doctors have learned how to interpret that. And yeah, it compiles in their brain, basically. But it's really hard to write down the rules that actually make that decision. If models or problems are just huge and the amount of the data to look through, genomics, think of all these genes that might affect some diseases or so, then also these kind of machine learning models are used and trained, as we see later on a little bit. Or if models change over time, think of traffic prediction throughout the day, that is really depending on a lot of factors. Also there, it's really hard to find actually rules that can be written down and then used as some kind of model. So this model that we will be using later then to predict something maybe is learned from given data. And if all of that is still a little unclear to you, we will walk you through today to what this really means at the end, what a model is and why there's rules and so on and so forth. On the contrary, learning is not always useful, obviously. For example, if you know the rules to solve a particular problem, there's no need to learn that. And in a minute, we will have an example what that also really means. So, for example, if you know how to solve a problem, in this particular case here, to calculate some mean, say, from a number of numbers, from some numbers, well, you can just calculate that, right? There's no need that you learn how to calculate that. It's just there. It's a rule, and you can obey it, and then you calculate some mean. So if you don't really know how to tackle a particular problem or to solve a problem, then oftentimes these machine learning methods are used to understand what's behind, or to at least get some kind of durations that you can be used to solve it at the end. But if you know exactly how to solve a problem, there's no need, and it doesn't even make sense and could even lead to worse results. There's no need then to use some machine learning kind of approach. So wherever you can solve a problem yourself because you know the rules, you should actually stick to that. It's much faster and much more precise. If you think about it a bit more formal, there was a nice definition by some guy called Tom Mitchell, professor in the area also of machine learning, some 20-something years ago. And he said something that is nice because it can be put into different parts. So he said, machine learning means to improve on a task T with respect to the performance metric P based on some experience. And forget now T, P, and E, but the point is that you can now define these parts here that I put in red and blue and then orange, yellowish. So there was, for example, one of the first approaches to AI, or that was first coined maybe AI already in 51 from the last century. And the task was to play checker, so some game. And the performance metric, so how good am I already, or what can I improve on, is, well, the number of games that have been won. So if you play more games and win more, then obviously your strategy becomes better, or your task, you improve on some task. And the experience that was used, or the data that was used to actually train that algorithm to learn from this data was, well, historic games. So the moves and the results. So that algorithm or that method looked at all these different historic games that have been played by someone else and try to learn some winning strategy maybe from that, because it knows all the rules and it knows all the moves and it knows all the results. Another example we also see in a second is, well, recognize handwriting numbers, and you will see in a second why this can be very challenging. And the idea here would be that the task is actually to do this recognition. So if I see a written number, a written digit, what is it really? Again, there's some performance metric. I need always to have something to understand whether my algorithm becomes better or worse, and then I have to do something else. Here, it would be similar as before, some percentage of the numbers that are correctly classified. So when I improve my algorithm, I see that this percentage goes up. And the experience E, or the data I'm working with, is, well, some kind of database of labeled images or human labeled images of handwritten numbers. So there's a handwritten digit 2, and then next to it, there's a label. So this machine can understand, okay, this is supposed to be a 2. The 2 can also look like this and this and this, so I better learn the general concept about it. And a third example, well, here the task would be to categorize emails. This is getting also, as you know, better and better over the last couple of years, but still not perfect. So I want to categorize emails for spam or real emails. And again, I have some performance metric that I can use to measure whether my model gets better, or it can make it better over some time, based again on some kinds like a percentage. And the experience E, or the data I'm using here, is again some database with humans labels or human given labels. And you see already from all of these results, there's always what is called a label, as in a human has created this knowledge and said, okay, this is the item I want you to, say, classify, in this case mainly, and here's the real result. So please learn how this is done. I can't tell you how it's really done, because as a human, I cannot literally say how this is done. My brain does something and that leads me to a result. Here's the results. Again, please learn this in between. How do you get from the input to the correct output? So this was then this machine learning task that I just mentioned. And here's again the idea of why it might be hard sometimes, and why it's also not, as a human, really clear on how to describe and therefore put it into a rule set on what's happened. So again, as we just said, I want to recognize handwritten numbers. And again, my metric could be this percentage or so. And this could be the database of these labeled images. So I know, because the labels, which I didn't write here now, but they were on the background if you wish. So this is 0, 0, 0, there's a couple of 1s, and it starts with 2, and so on and so forth. And as a human, we probably recognize all the 2s. Although maybe with this one, could even be a 7 sometimes, and the 7 could maybe even be a 2 here. But more or less, humans can understand what the digits mean. And now the point is, and this is one of these classic machine learning tasks, if you don't really know how to do this, there is no real thing as in, well, there has to be some particular angle from here to there and here to there, because here it's super different. But there seems to be some kind of concept. And there's some kind of concept that I cannot really describe as a human, maybe parts of it, but not fully. This is then the idea to train a machine. So machine learning, train a machine, machine training, machine learning, all the same thing. And now the real machine learning task is, well, if I give you this kind of little image here, then give me the result, and I give you my experience or my data, which is this database of handwritten numbers and the correct labels. And then the machine figure out how this is solved. This is, in a nutshell, what really machine learning is about, and we will hear a bit more about details today. Then, of course, no talk can be without some milestones or history, and I just picked out some of them. So this is not mine. I stole it from this guy here. But there are some milestones that are interesting. First, there was this, what I just said, this checker game that was already written in 51. And it was one of the first AI-based programs, actually, that are at least known. Then there's something like the first machine learning program, or in 63. And that was actually learning tic-tac-toe. So there's a lot of games because they're good to also put in rules, but then you see and watch how the machine learning is actually doing about it. What you today know about chatbots from ChatGPT and what they're all called, that already also had some faraway ancestor, if you wish, in 65 already, called ELIZA back then. If you want to read about history, it's a nice read on Wikipedia and others. But even that was existing 50 years ago, 60 years ago. Then what changed a lot of people's shopping life, Amazon and all these big companies, they developed or found, if you wish, what is called recommendation engines, also big movie streaming like Netflix and then others, which is at the end nothing else than if I analyze what a lot of other people actually bought and I see what you are buying or watching, then I can recommend you stuff that's really interesting to you because it fits to your history. And that might or might not sometimes work, and sometimes it works just worse, and then going randomly basically. But this was one of the first times in 2005 where these things became really apparent and on all these shopping sites. And there's a really large effect that you can see from that time onwards, where people bought stuff that they probably didn't plan to, just because these recommendations had become so much better, and said, hey, this might also be interesting to you because I know what you bought before. So it even has an impact on society. And then something that also some people might not, at least not connect to these days, in 2015, OpenAI, what we know today of the creators of ChatGPT and others, was founded. So a little bit then, or almost 10 years ago. And they started out as a really non-profit kind of open source initiative or crew team that was supposed to start something in this AI context of machine learning, of how machines can also train themselves and so forth. And they ended up developing language models, which we know today to be one of the really groundbreaking milestones that we had in the last couple of years in this business. Rest of these things you might want to read yourself later. The slides will be available, I guess. So a lot of things happened also throughout. There was the first self-driving car in 2000 already, and so on and so forth. And the last couple of years were mainly dominated by generative AI, as it's called today. So AI that is able to generate photorealistic images, videos, reports, everything connected to language. Since GPT-3 came to life, I was about to say, or was presented first. So everything that can generate things that are sometimes not even distinguishable from what humans would do, or a photo camera would take as a picture or as a movie. This is over the last couple of years mainly the driving force behind all this. And today a lot of things that is actually already in our everyday lives, whether it will be something in the area of segmentation. So you have now in many mobile camera or mobile apps on mobile phones this eraser kind of magic or magic eraser kind of function, where you can just say, okay, I have a picture, but I don't want to have that person anymore in there. Please erase it or generate the background so that it fits to the rest. So that's oftentimes backed up by something called segmentation. So what is happening in the picture? What are the different elements in there? And this became increasingly well done, such that you can really segment out cars or trees or I don't know what in whatever images, or just a little bush in some forest image you can just take out, and the algorithm creates or generates what should be seen there, and it fits just perfectly. Poster recognition, also quite important for a lot of applications. How many humans are there? How do they look like? What are they doing? Are they typing something? And these kind of things. Semantics is increasingly important also for robotics these days, where you just have an image and you can query that image, as in this example here, what is in front of the sofa? And then, well, the round truth would be a table. There was this here or this table there. And these models these days, most of them at least that exist, can answer these questions almost perfectly. How many leftovers donuts are on the red bicycle? So this thing, and then 3, and then most of the algorithms at least say something, all being correct. And today's top performing algorithms get more or less everything right. They are really on a human level these days. Other things connected to speech also, I mean, Siri was introduced, and then also Alexa was introduced some years ago. But these days, not necessarily Siri and Alexa, but other algorithms that are on we are working in the same field basically. From again these ChatGPT kind of models, they are almost perfect. They can deal with dialects, they can deal with really people who is not their native language, and they can still get more or less everything perfectly right, even better than most humans can actually do. And all that is fueled or fed by something AI, something machine learning, and the algorithms that have been trained to, or by experience by humans saying, look, this is a sentence that was spoken, this is the actual text. Now please just learn how this can be converted from the words that have been spoken to the real text. And this has been trained with these large models, and these days almost perfect. Other applications include most domains you can imagine. E-commerce, we had healthcare. There's a lot of things happening in healthcare that is fueled or powered by, or whatever you want to call it, AI and machine learning these days. Financial services, transport, from air control, as we also had earlier, prediction of traffic, social medias. In the best case, it's just filtering spam. In the worst case, it's robots that are trying to make you take over some opinion. Super dangerous stuff. Works also surprisingly well these days. Scary things coming up. As we said, trading, if you are into stocks, then you might want to look at these new robot traders. They're also becoming increasingly popular and good, because they have all this incredible amounts of data they have been trained on, and they can just see that human just can't see anymore. So if you have hundreds of thousands of pages of business reports or moves in stock market things, these algorithms are trained to just understanding not in the human way, but to find the patterns, and based on the patterns, then do some predictions of what might happen in the near future. Machine learning, AI, artificial intelligence is everywhere these days. There's really no way of not using it on an everyday basis, even if you just have a smartphone or switching on your TV. Even that will be used to somehow, or at least on most TVs these days, to monitor and measure your changing of channels and watching commercials and so forth. Okay. Then you might see that I'm using sometimes the words artificial intelligence and machine learning interchangeably. That is because of this. So basically, when you talk about these concepts, then artificial intelligence or AI is roughly speaking the whole thing, right? So everything that enables machines to mimic human behavior, this is what we usually call AI. Machine learning is a subset of AI, and which is in most cases or almost all cases based on statistical methods in some way. And we will look through 2 or 3 of them today, briefly at least. And the point is, and this is what makes machine learning, that it can improve with experience. So that's what we said earlier when we talked about these measures that they can be used to check whether they're becoming better in some way. So winning more games, having more digits correctly classified, and so forth. So machine learning is really defined as I can learn a model and I can improve it the more data or the better data that I get, or experience data in this case, the same thing. And then there's deep learning, which we will look at in 2 sessions from now, which is again a subset of machine learning. and is based not necessarily on statistics anymore, although this is debatable whether or not statistics plays a role there, but it's based on so-called neural networks, and we will also have a look at that in 2 weeks from now, or two sessions from now. So this is really the idea. Therefore, AI and machine learning is sometimes reused interchangeably because machine learning is just a subset of AI in somewhere. So AI is just the big area overall. Okay. So what's need to be understood, or what's important in this whole thing is machine learning is entirely data driven. We had that before, right? You have some kind of model, you want to learn something, but this learning is based on the data, on the experience that you give that model to learn from. And then which model or which type of learning you really use at the end, and we will look at some variants later, is depending maybe on the use case itself. But what is driven or what is driving machine learning is the data, the experience that you give it, basically. So that's really the idea. Let's look at some example. In the traditional kind of programming, or in the traditional programming world, maybe is what I also said last time very briefly, is that you have some data. Sure, there's always something about the data, but at the end of the day, you already built a program that knows how to deal with data. So you said, if I want to do this, then these are the 3-4 rules that have to be done, or this recipe that has to be followed, and then there will be some output. And I'll give an example in a minute. Machine learning, on the other hand, is different. The program that is developed, so the model, the machine learning model that can do something later, predict whether there's a traffic jam at 3 p.m. today, or whether I should invest in that stock, or whether this is the disease that I might have also given my data. The program is developed through this training, through this learning steps that I mentioned a couple of times now. So the idea is you feed the machine learning algorithm or model with data. You feed it with the output. That was the experience I mentioned earlier. So this is how a 2 looks like. Here's a 2. This is how 3 looks like. That's a 3. That's how a 2 looks like. That's a 2. And then your program, your model, figure out how to get from the data that gives you the input, say the handwritten digit, to the output. This is a 2. And this program or model, whatever word you like better, is then created through this process. Okay. So traditionally, we write the program, and the program is using some data. And the new world is, new world, I mean, we saw already since the 50s. The new paradigm, maybe, or the different paradigm, is that the data and the output together are fed into something, and out comes a program or model that can solve a particular task. If you like flow diagrams better, then maybe look at this. Just the same thing as before, just a different explanation. So in the traditional programming, we have some problem at hand. We code the rules, we know what we want, then we evaluate our program. If it fails, well, we'll review the errors, maybe change the rules somehow, but we are in control of everything, right? We put the rules in there. And once we're happy with it, we put it to production. In machine learning, it's different. We have a problem. We have some machine learning algorithm that can learn, and that's now the point again, from data. We have this training data or experience or just data that it can learn from. We train our model, we tell it again, this is a 2, this is a 3, this is a 4, that's a 2 again, that's a 3, that's a 7. Learn what I show you. The program learns it somehow, and then at the end we can evaluate it. If it fails, well, we review the errors, change the algorithm a little bit, maybe get new data, train again, evaluate until we're happy, and then we put it to production as before, and then we can use it in our everyday lives. Again, that could be prediction of traffic jams, a medical doctor support system, and so on and so forth. Okay, let's do an example. Let's assume something stupidly simple and think about how to convert Celsius to Fahrenheit, because that's an easy problem. So as we know, we can measure temperature in different units, so Fahrenheit, Celsius, Kelvin, and so on and so forth, and even more, I believe. They have different scales, if you wish, right? So what is 0 degrees Celsius is 32 degrees Fahrenheit and 273 degrees. And what is a so-called model, or a mathematical model maybe for that, or the most general form of something, is a function. So you put in some data point x, then you apply a function to it, this f here, that is acting on x, and out comes some y. So you put an x and you get a y out. And the question is, what is this f here? What transforms my x to a y? And this f here is either a rule, and this is what we will see next. So we can say, look, sure, I know the rule. I know how to calculate Fahrenheit from Celsius. Or you can learn this f. And this will be then your machine learning part here. And I can train this f, or I can learn this f from all the data. And then my f is basically my machine learned program at the end. So how does it work? Classically, as I said, you don't need to learn anything, you just know how it is, or you go to Wikipedia or somewhere else and say, okay, what is the model that I want to use? And okay, I know the model is 1.8 times degrees Celsius plus 32. That's what Fahrenheit is. And then you can put it in some code. Here's some Java code, doesn't matter. And you have your program ready, right? You know the rules. You can write a program. That's it. You get an input. And once you have the input, the Celsius, you can calculate exactly what the Fahrenheit is. That's what the classical approach was. I know how to do it. I know the rules. My model is, well, as it's naturally or from these systems at least given. How would that look if I want to do machine learning on it? If you do machine learning on it, you know that, because I said earlier, you need now data, the experience, and you want to learn this function that translates the Celsius to Fahrenheit. So what would you do? You would collect this data or create this data or get the data from somewhere. For example, you could take two of these, what's it called? Thermometer in German, and you would put them outside, two of them, and then you would just every minute or so, or maybe every hour or every day, you would look at these two thermometers and just write down the numbers. So on the one axis, you have the Celsius, and on the other hand, axis, you have the Fahrenheit, and you would put just the dots here, roughly speaking, of these two coordinates. So now you have some data collection where you say, okay, if I have 30 degrees Celsius, then it's about 60 degrees Fahrenheit. This is data that you collected. Problem with the data, as you see, there seems to be some noise in there. It's not exactly what it should be. Sometimes values seem to be not correct, at least if you know what you're looking for. However, this is now the data that you have. That's as good as it gets. And now what you can do is you can learn a function that translates, again, that was the aim, that translates your Celsius to Fahrenheit. And this function will be this red line here. Why? Because this is a red line that best resembles, if you wish, all your dots. So it goes exactly through the center of all these dots. So if you calculate the distances from every point, every blue dot to the red one, this will be the line where this distance is minimized. So if you just want to remember, rough idea, you have these lines and you put this kind of regression line through it. And now this red line is your model. So if you now put in 10 here in Celsius, then you go see how it hits the red line. Then you go to the left and find out it's 40 something, 47 or so Fahrenheit. And this is then what you got. And then if you now just find out what this red line means in numbers, you will see that this is similar to the actual term that you had before, but there is some kind of error. This was this spreading around, this wiggling around. So this stochastic model or this learned model or this machine learned model is not necessarily exactly true because there is some kind of error that came from the measurements. And this is one of the most important messages from today. If you were able to collect data perfectly, so no errors on your data, you would get perfectly back what should be in there, right? So the conversion from Celsius to Fahrenheit would be exactly coming back from your model. Since in most cases, at least, your data is not perfect or not error-free, your model might be a little different, say this error might be 0.1 or so, so your model might be a bit off of what the real model would look like, of what is the actual translation from Celsius to Fahrenheit. However, if you don't know how to translate Celsius to Fahrenheit, so you have no idea about this model here, this is the best you can do, and well, you get something back that is actually quite decent, right? So the idea, again, if you know how to do some particular transformation or have a model about something, there's no need to do machine learning. But if you have really no clue of what this Fahrenheit is, you just are told there's two different systems and I want a translation formula or a translation model, then this is more or less how machine learning works. You would collect the data, You find this, in this case, linear model, and there you go. You have some idea of what your program looks like that you just learned from this data. A lot of problems with that. For example, who said that this is a straight line? Well, it looks like a straight line. Okay, so that's why we chose it. In other cases, it might not really be true. For example, if your collected data would have looked like this kind of sine or cosine function or so, then you could start with some linear model again, so a straight line, and this would definitely not be correct. It would be not complex enough to actually resemble the data. This one here would be almost perfect, I would say, in this particular model that you choose. You can choose too many parameters and you perfectly then fit your blue dots with your model, but obviously that doesn't make any sense here. So the point here is that you, as a user or as a person who's training this machine learning stuff, needs to select a model. So you need to say, okay, that's the model I want to use. And then the training part is whether or not you move the model a little bit around. So this line here, you could move it a little bit up or down, or you just tilt it and make it like this or so. So how the model is then parameterized, as we call it, so in which direction, for example, it goes, this is the training that we do. But the model shape, whether it's a straight line or this kind of shape here or so forth, this is determined by the user. So in machine learning, a lot of the gray magic later will be to find the right model that matches your data. And this can be because you tried everything possible, 10, 20, 30, 100 models. Or this can be because you were purely lucky, or you knew how that looks like, and from experience, you know which model to choose for. But this is the key idea. So machine learning tries to fit some kind of model to data. Which model is, in this example, a straight line or something trigonometric or so, is really then the art at the end to select the right thing. And then to fit that model perfectly to the data to maybe actually make this a little bit going to this side here or this to this side. So the actual form of the model that you can bend a little bit if you want. This is then the training part in which you make your model fit to the real data. Quick spoiler or teaser, when we look about deep learning models later on neural network models, then these kind of models can be fit to almost any data set that you can imagine. So there's no real reason to choose or to come up with the real shape of the model that you would like. These deep learning models are more or less generalizable such that they can actually fit every data set that you can imagine. So there's a large of the problems actually goes away there. You get other problems, but at the end of the day, deep learning is much more general class of models than all the stuff that we see today. Okay. So I said there's many models you can choose from and many types of things or learnings that you can actually do. And if you just look at a simple version, at least, of the machine learning family tree, you will find that there is a lot of words that we will definitely not discuss today, but you might have heard before or you will hear in your later life. But the classical part of machine learning actually only includes two large areas, which is something called supervised learning and unsupervised learning. And then there is a lot of other things, patterns, clustering, classification, and so forth. We will not go too much in detail today, but the main message I want to get from this picture is that there is a lot of machine learning, a lot of machine learning types, a lot of machine learning algorithms. In fact, I would even say thousands of different ones. But the real classical approach with its two large directions is supervised learning and unsupervised learning. This is also a famous question. If you apply for some machine learning job, one of the first two questions will be, okay, just tell me the 2 or 3 main directions of machine learning. And then you say unsupervised and supervised, and maybe reinforcement learning. Sometimes that's what they want to hear, but that's basically it. So just to say, okay, this is really the main directions in machine learning. Now, what is that? Supervised learning is actually super simple. We discussed that last time a little bit, and I also mentioned it earlier today. In supervised machine learning, you provide the machine algorithm with what we call labeled input. So we say, look, well, these are cats. This is a 2. This is a 3. So we have a label for the data. And we tell it, dear machine, please learn now how to, in the case before, from Celsius to Fahrenheit. If I now give you an image, tell me the label. If I tell you an image that looks like a 2, tell me it's a 2. If I give you an image of a dog, well, tell me it's a dog. And then, so this is how I train it. And then step 2 is then, okay, I give you now images that you haven't seen before, dear algorithm, dear model. And then please, again, tell me what it is. And based on that, I can evaluate whether the machine learned what I wanted to learn. So if I train it on cats and I'm just interested in cats or no cats, then this might be enough already. I feed it different pictures and it will say, well, that's not a cat. And I'm happy with the results and I can even measure how good it is and so forth. But this is supervised learning. I know the data, how it looks like, and I know the real labels to it. That's a two, that's a cat, and so forth. And well, it suits in basically in 2 ways. One is classification. That's what we also discussed last time a little bit. So the idea is I have, say, cats and not cats, and I just want to have a class, in this case, cats and not cats, and this classification problem can be multiple classes, can be just all the animals that exist, and that's what's supposed to learn. Whatever you want, this is classification. Or the other type basically is what's called regression. And in regression, we learn, for example, something as in we tell it how big a house is, and the thing should learn how expensive it is. And then I can train it with a lot of real estate data, a lot of houses that have been sold and how big they were and how expensive they were. And then the model learns this, what's called regression. Or in the earlier example, this could be Celsius to Fahrenheit. So it needs to regress, okay, this much Fahrenheit is this much Celsius, and it just learns this correlation. The second one is unsupervised learning. Unsupervised learning does not have labels. That's the only difference, and therefore the main difference. So the idea is I give the machine a lot of stuff, a lot of images, for example, and I just wanted to put together what is close. So in this particular example here, I give it, pictures from dogs and cats, say, and it doesn't know what it is. It just tells me or gives me as an output, well, all these images are somehow similar, or these images are somehow similar as well, but an image from this group and in this group are not similar. So that's really the only output that we get. And that's also what we discussed a little bit last time. There we thought about having papers, for example, scientific papers or books or articles, and we give all them to the machine and let it group. And then we check, oh, the article I like is in this particular group over there. Well, maybe I should read more articles that are in this one group. So I'm interested in how these groups work together. You can think of medical examples where you group patients together and see whether this somehow correlates with some respondents to some drug or so. So then you can dig deeper afterwards in the analysis and say, okay, why were they grouped together? Why do they respond better to a particular strategy or drug or so? Anomaly detection, if you have, for example, credit card fraud, then you can say, okay, all these transactions seem to be normal, all these over there seem to be different, so it could be maybe some hacking or whatever else, and you can identify these groups just by looking at the data. So these are the 2 main things, supervised learning, unsupervised learning. Again, the 2 main things. There are dozens, if not hundreds, of other ideas, but these are the 2 main things that usually, are okay for 70–80% of the use cases that one has. Good. Last part of today is to just go through some example machine learning project, just to get the idea of the main steps that are in these kind of projects. Again, we'll not go too much into details, a little bit more than in the next session. The idea is for now that you just understand, okay, this is the stuff that I need to understand, or at least the steps that I need to follow. How exactly this might be then in a different session. But yeah, these are the main things that machine learning is. So on the left-hand side will be always the steps that are important. We will go through them step by step. And on the right-hand side is always some explanation. Okay. So atypical, this does not mean that every machine learning project is really like this. Sometimes it's a lot more about data and data cleaning and taking care of the data and bringing them to a form that is usable and so forth. But the main steps are more or less always the same. So it starts with a problem or task definition. Then we talk about data. Then we choose some model that we would like to use, machine learning model in this case, and we train our model, evaluate, improve it, and then, well, at the end, present results or present some knowledge to be good. Let's go for a super simple, understandable task, I guess, totally made up, but it's also on the internet a couple of times. So there was a lot of material about that if you want to go for it and check this a bit more details. Some friend of mine, Sarah, likes weekend sailing, but not under any condition. For example, if it's too stormy, well, then she doesn't go sailing. I usually enjoy going with her. So if she goes on a weekend, I'll usually try to then go with her. But in the last weeks or month, it was often the case where she said on a Friday, oh, I will go on a Wednesday or whatever, and then something happened and then she didn't go. So to plan my weekends a bit better, I would like to understand her behavior. So when I see on Friday all parameters that I know at least on that, so the data that I can gather, then I would like to be able to make a prediction whether on Saturday she will actually go sailing or not. Okay, quite simple. So I don't want to understand the person. I just, based on the data that I can collect, I want to predict her behavior on the next day. That's the task. So given some data from, in this case, Friday, predict whether Sarah will go sailing on Saturday, actually, whether she will do that. Good. What do we need? We need data. So the last 20, say, Fridays, I have asked her on a Friday whether she will have some kind of companies or some other friends that go with her, which boat she could actually rent on a Saturday, and I checked the weather forecast. So that's what you see here. So weather forecast for the next day, rainy, sunny, and so forth. Does she have a lot of friends or a big company or a medium or no one who goes with her at all, and so on. And I have checked which sailboat she would be actually able to rent on Saturday. So the big one, a small one, and so on. So that's the data I've collected, right? Already on Friday. So Friday, I have now these three parameters, the outlook, the company, so the people are joining her, and the sailboat. And since this is a retro perspective, I also know the answer. So I know what she then did on the Saturday. So all this is from Friday connected to stuff I know then from Saturday. So I know if the outlook on Friday was rainy and the company, well, she was supposed to go with many people, other people, and she had a big sailboat, then she would go sailing and so on and so forth. So that's the data I have. So now what I want to do is I would like to train an algorithm that based on this data and these results that are coming from this data on the next day is able to do the same thing. So if I feed then the algorithm or the model with, well, outlook is sunny, company is low, so it goes to her, and the sailboat is big, then I want the model to tell me most likely she will not go sailing. So this is now the machine learning part. I have an algorithm, a machine, a model, and I train it with the data that I have here. Now comes the crucial part that I said also earlier. Which model? Is it the straight line? Well, obviously not here because there's multiple parameters, or is it a curve or so forth? So we need a model that can predict this column here based again on the available data. And this is now, once again, this gray magic part. Now I need to choose from hundreds of different algorithms that I would like to use or to train or that they learn this data that I have at hand. Can be any. Can be really everything more or less from this page here. Can be really anything else. We heard regression earlier. We had decision trees. Whatever you want. This is now the point. Choose something. Experience shows you from maybe earlier projects or lectures that you attended which one to choose. In this very particular case, we will go for something called decision tree because I know from experiments that for this data, this actually works well. But I could have done anything else, train it, and see how it works. Good. So I chose a decision tree. I trained the model with the data, and this is what comes out. This is what's called a decision tree. So my first decision is based on company. So if the company is medium or no, I will go down the tree on this side. If the company is big, I will go down the tree on this side. And how the tree looks like, how many of these inner nodes and so forth it has, is learned from the data, right? If the data would have been different, this tree would look different. So this tree is the model or the program that is learned. I told that whole procedure, hey, learn the tree for me. And then I told this tree learning algorithm, here's the data, give me the best tree back. And again, this is what it came back. So I know if her company was medium or non-company and the outlook was rainy, she wouldn't go sailing. I know if the company people are going with her is big and the sailboat was big, she always goes sailing. So this is now the decision tree I can do. So it's quite interpretable. It's nice to see. I can understand most of it. And again, it resembles the data that I have as good as possible. And to do this, under the hood, there's some kind of algorithms, some search algorithms, doesn't matter for now. But these algorithms actually learn the actual structure of the string. Then I can evaluate my model. I can just check, okay, how good is it? And I can use, that was this matrix that I also had earlier. I can choose whatever I want to evaluate. In this case, I'm interested in accuracy. How accurate is this model, this tree that I learned from the data? This now assumes that I have 365 observations. So for every day, yeah, I had one, which is a different example. Bear with me, numbers are not the same as before. But the point is, I can now have this kind of table that's kind of a confusion matrix or confusion table. And I can say, okay, if the true class that she goes sailing was yes, what did my algorithm say? And the algorithm predicted also yes. Cool. If the true class was correct, if the true class is no, and my algorithm also predicted no, great. That's this many that happened. And then, so this is everything that is correctly predicted. So it was yes, it predicted yes, it was no, predicted no. And these are the ones that are wrong. So the true class was yes, my algorithm said no, well, it's clearly wrong. And my algorithm said no, true class was yes, well, 12 times it was wrong. And now the accuracy is quite simple to add up. So it's this diagonal here added up, divided by the total number of cases that I tried. And I get back, well, 96% of all the cases that I looked through were correct. So the accuracy of my model is now 96%, something I can work with. And now I have some idea of also how to compare to something else. So if I now had a different tree that looked differently, I can say, okay, the accuracy of the other tree is say 89% or 50%. So I better go with this tree or this model because it's clearly the better result. I left in these following two slides because you can then have a look at it later if you want. Now, the actual improvement of the model, if I know it's not good enough, would be broken down into what we call reducible, irreducible errors. So irreducible we can't do anything about. Reducible errors is where we can improve our model. We can break that further down to something called bias and variance. We will look at that in the next session. Just for the sake of completeness, I put you also a slide in here, some kind of cheat sheet, what everything means. But for today, that's not the focus. So the important part is I have a model. I trained it on the data that I prepared. I created this tree that was then the outcome or the result. I evaluated it. I know how good it is. And now I have a model. I have something where I say, okay, that's the best model, the best tree that I can come up with. And now I can even look at this model and present also results and not the model itself, but I can also get some insights from it. In this particular case, I could derive from it that Sarah's actually a social person. When the company is big, she goes always sailing and she has a big boat. It was this part here. So if the company is big, then it's here. So even if the sailboat is big or small, she always goes sailing. When the company is smaller, she would not go sailing if the weather is bad. And when it's fun, when it's sunny, then she always goes even when she's alone because sailing is fun. So this is then something I can interpret from the model that I learned. But the learning itself was done by this machine learning algorithms. Okay. Also, quick comment about data. I will not go into too much detail, but it's important that you heard it once. The trained data or the data that we are training with is called this original data set. And what's happening in the machine learning part is that we train only on a part of the data. So say we have 100 data points, so 100 weekends where I have Sarah's behavior about the sailing. Then I would train on, say, 2/3 of it, or the majority of it, I would use to train my model. And the other 30% or whatever we chose is what's called a testing set. And this is how I then actually validate my model with. So I test on the data the model has not seen during training to prevent it to just memorize all the answers that are correct. Right? And again, next time we will go a bit more details here. But the important part is from all data you've collected, only say 2/3 or 70% or so is used for actually training the model, and the rest is used for saying how good the model is at the end to get some kind of independent set the model has not seen before, and I can make sure that the model just didn't memorize the answers, but actually learn something from the training data I gave. Okay. And that brings us already to the summary, because also time is up in 4 minutes. First comment again, we will do this hands-on next week, where we try to go through this Sarah's example, the sailing example, and you'll see how we do this actually in programming. So please bring your Google Colab account. And then having said that, what we did today is basically going through this pipeline here at the bottom. So I showed you there is some data that you need. I didn't, or I skipped over the part on what really preparation would mean. We go through that a little bit next time. Then I showed you, okay, you have to choose a model and you have to train this model. How exactly is still somehow blurry in the clouds. But the point is that the model learns on how to go from something I present to it to the real label. So it learns if I show it, that is a 2, that is a 3, that is a 4. It learns how to actually go from this handwritten digit to the actual label at the end. I mentioned a little bit of how to optimize it, so give it maybe more data or better data, so it actually can learn a bit better. I showed you quickly, briefly, how to evaluate this. This was this confusion matrix, how many were actually correct answers, how many were wrong, and then we could derive the accuracy from it. So how good is the model actually? And then, the last step would be deployment. So using it actually in real life, or just use it for my own fun, that I want to predict what Sarah's doing actually. So I can then use the model that I developed. Or if any of these steps will fail or I'm not happy with it, I'll go back. If the model evaluation is good enough, I might go back to even choosing a different model or getting more data or better data or so. And this is in the pipeline that typically machine learning people or data scientists are actually doing. Yeah, and then the overall summary is machine learning is programming computers to solve a task we had while improving a particular criterion. That was the evaluation, the accuracy, for example, using, and that's the important part here, data or this past experiments that I collected to somewhere else. Good. And with that, I'm this time even done before the time. Thanks for listening. We have 2 minutes for questions if there are any, and if not, I see you next time.
Yeah, so just a couple of moments to get you additional information. So if you have any questions, please ask in every way you are comfortable with. If you don't have any questions, you will now be offered, when leaving this session, you will now be offered to evaluate this webinar. So please do it. We will get this information to improve our way of learning. So this is very important for us. And also, as you may notice, this session and the previous one were recorded. So all this information will be available on YouTube later this week, probably. So please join our LinkedIn account. All the important information and updates are available there. Thank you, and thank you, team. If you have any questions, please ask.
Good. If that's not the case,
yeah.
have a great day.
Yeah.
See you next time.
See you. Bye.